The trajectory of aeronautical engineering in the first half of the 20th century was neither linear nor guaranteed. While the popular imagination often fixes on the daring of pilots or the industrial might of manufacturers, the true fulcrum of aviation progress lay in the invisible, often counterintuitive physics of the atmosphere itself. By the late 1920s, the propeller-driven aircraft had reached a sophisticated plateau, yet the path forward was blocked by a formidable, invisible wall. This was not merely a barrier of speed, but a barrier of understanding. As aircraft approached velocities exceeding 400 miles per hour, they encountered violent instabilities, inexplicable drag rises, and catastrophic structural failures that defied the classical laws of aerodynamics established by Newton and Bernoulli. Into this breach stepped John Stack, a figure who would become the single most influential aerodynamicist of the mid-century American aeronautical establishment. Stack was not merely an engineer, he was an architect of research infrastructure and a strategist of technology. His tenure at the National Advisory Committee for Aeronautics, NACA, and later the National Aeronautics and Space Administration, NASA, bridged the era of the biplane and the era of the Mach 2 interceptor. Unlike his contemporaries, who often specialized in narrow subdisciplines, Stack possessed a holistic vision that encompassed theoretical physics, experimental facility design, and flight test operations. This report provides an exhaustive analysis of Stack's contributions, positing that his genius lay in his ability to identify blind spots in aerodynamic knowledge, specifically in the transonic regime, and to construct the physical and intellectual tools required to illuminate them. From the identification of the compressibility burble to the design of the Bell X-1, and from the revolutionary slotted throat wind tunnel to the variable sweep wing, Stack's career is a roadmap of the solutions that made modern high-speed flight possible. His unique distinction as a two-time Collier Trophy winner, once for a vehicle that broke the sound barrier and once for the ground facility that made such vehicles routine, underscores the duality of his legacy. He was the master of both the air and the wind tunnel. John Stack was born in September 1906 in Lowell, Massachusetts, a city that was, at the time, a pulsating heart of the American Industrial Revolution. Growing up amidst the massive textile mills and hydropower systems of the Merrimack River, Stack absorbed the ethos of heavy industry and mechanical pragmatism. His early interests were kinetic and visceral. He was drawn to motorcycle racing and amateur radio, hobbies that required a hands-on understanding of power, speed, and invisible transmission waves, themes that would echo in his later work with propulsion and shock waves. In 1924, Stack enrolled at the Massachusetts Institute of Technology, MIT. Interestingly, his initial trajectory was not toward the skies, but toward the built environment. He entered as a student of architectural engineering. This initial grounding in architecture perhaps explains his later talent for structuralizing research programs and designing massive wind tunnel facilities. However, the rapidly evolving field of aeronautics captured his imagination, and he switched majors, graduating with a degree in aeronautical engineering in 1928. Upon graduation, Stack joined the Langley Memorial Aeronautical Laboratory, LMAL, in Hampton, Virginia, as a junior aeronautical engineer. In 1928, Langley was the only research center of its kind in the United States, a monastic collection of brick buildings and steel wind tunnels located on the fringes of a humid marsh. The culture at Langley was unique. It prioritized the data above all else. It was an environment where theoretical speculation was rigorously checked against experimental reality. Stack was assigned to the Variable Density Tunnel, VDT division. The VDT was the NACA's crown jewel, a pressurized steel tank that allowed engineers to test scale models at pressures up to 20 atmospheres. This capability allowed the simulation of full-scale Reynolds numbers, a dimensionless quantity describing the ratio of inertial forces to viscous forces in a fluid, thereby solving the scaling problems that plagued other wind tunnels. Working in the VDT division, Stack was mentored by luminaries like Eastman Jacobs, who instilled in him a relentless pursuit of precision and an understanding of the boundary layer, the thin sheet of air clinging to the surface of a wing that determines its lift and drag characteristics. By the late 1920s, aerodynamic theory treated air largely as an incompressible fluid, similar to water. This assumption held true at low speeds, below 200 miles per hour, where the density of the air changed negligibly as it flowed over a wing. However, as racing seaplanes and early monoplane fighters began to push speeds higher, pilots reported strange phenomena: heavy controls, buffeting, and a sudden refusal of the aircraft to accelerate despite increased power. Stack was among the first to recognize that these were not mechanical failures, but symptoms of a fundamental shift in fluid dynamics. He understood that air is compressible. As an object moves through it, it sends pressure waves ahead to warn the air to move out of the way. These waves travel at the speed of sound. As the object accelerates, it begins to catch up to these waves, causing the air to pile up and compress. To study this, Stack helped design and operate the 11-inch high-speed tunnel. This was an induction tunnel, using the violent release of compressed air from the VDT's waste tank to induce high-speed flow for short durations, often less than a minute. It was crude, but it was fast. In 1934, Stack achieved a pivotal breakthrough. Using a Schlieren photographic system, an optical technique that visualizes changes in fluid density, he captured the first clear images of shock waves forming on an airfoil in a wind tunnel. These grainy images were transformative. They showed that even when the free stream velocity was subsonic, e.g. Mach 0.7, the air accelerating over the curved upper surface of the wing could reach supersonic speeds. Stack observed that where this local supersonic flow was forced to slow down to subsonic speeds, a shock wave formed. Behind this shock wave, the boundary layer of air separated from the wing surface, creating a turbulent, chaotic wake. Stack termed this phenomenon the compressibility burble. The burble was effectively a stall, but one caused by speed rather than angle of attack. Stack's analysis in reports such as the compressibility burble, NACA TR 592, and the compressibility factor, 1935, detailed the consequences of this phenomenon. Drag divergence. Drag did not increase legally. It skyrocketed exponentially as the critical Mach number was exceeded. Loss of lift. The separation of airflow behind the shock wave destroyed the suction on the upper wing surface. Mach tuck. The loss of lift on the wing, combined with changes in the downwash hitting the tail, caused the aircraft's nose to pitch down violently on condition that could become unrecoverable in a dive. Stack's work in the 1930s laid the theoretical foundation for the crisis that would engulf combat aviation in World War II. When P-38 Lightning pilots began dying in high-speed dives, it was Stack's theory of the compressibility burble that explained why their controls locked up and their tails were torn off. Recognizing that the 11-inch tunnel was too small for detailed pressure measurements, Stack pushed for the construction of the 24-inch high-speed tunnel. Operational by the mid-30s, this facility allowed Stack to test a new family of airfoils. In 1938, he published tests of N85, N86, and N87 airfoil sections, which introduced the NACA 16 series airfoils. These designs were radically different from the thick, high-lift wings of the 1920s. They were thin, with the maximum thickness moved further aft to delay the acceleration of airflow and thus delay the formation of the shock wave. This concept, designing specifically to raise the critical Mach number, would later inform the wings of the P-51 Mustang and the Bell X-1. By 1940, Stack faced a methodological crisis. Its high-speed wind tunnels, including the newly repowered 8-foot high-speed tunnel, HST, suffered from a fatal flaw known as choking. As the airflow in the tunnel throat approached Mach 1, shock waves would form and reflect off the tunnel walls, striking the model and corrupting the data. This created a transonic blind spot between roughly Mach 0.75 and Mach 1.3, where wind tunnels were useless. Engineers resorted to desperate measures: drop bodies, dropping weighted models from B-29s to achieve terminal velocity through the transonic range. Wing flow method, mounting small models on the wings of P-51s, using the accelerated flow over the fighter's wing to simulate transonic speeds. Stack viewed these as inadequate stopgaps. He believed that to understand the transonic regime, one needed a laboratory that could sustain flight conditions inside the burble. Remarkably, Stack had proposed a high-speed research airplane as early as 1933. At the time, propulsion technology, propellers, could not support it. By 1944, with the advent of the jet engine and the rocket, the concept was viable. Stack found a counterpart in the Army Air Forces, Major Ezra Kocher. Both men agreed on the necessity of a manned research vehicle, but they diverged on the propulsion. Stack, prioritizing data collection duration and safety, advocated for a turbojet-powered aircraft. Kocher, focused on raw thrust to punch through the drag rise, argued for a rocket engine. The result was a two-pronged approach. The Navy NACA D558 Skystreak, a jet-powered aircraft, Stack's preference. The Army NACA XS-1, Bell X-1, a rocket-powered aircraft, Kocher's preference. Stack played a dominant role in the aerodynamic configuration of the X-1. While Bell Aircraft, Lawrence Bell and Robert Woods, built the machine, the outer mold line was dictated by Stack's compressibility data. The thin wing. Stack insisted on a wing thickness-to-chord ratio of 10% or less, far thinner than contemporary fighters, to mitigate shockwave formation. The all-moving tail. This was Stack's most critical contribution. He and colleague Robert Gilruth predicted that as the X-1 approached Mach 1, a shock wave would form on the horizontal stabilizer, rendering the elevator ineffective, a phenomenon known as control freezing. Stack insisted that the entire horizontal stabilizer be movable to provide pitch control when the elevator failed. This feature saved the program. On the record-breaking flight, Yeager lost elevator authority but maintained control using the moving stabilizer. On October 14, 1947, the X-1 broke the sound barrier. The achievement was a vindication of Stack's belief that the barrier was a steep hill of drag, not a solid wall. The 1947 Collier Trophy was awarded jointly to the three pillars of the program, representing the symbiosis of government, industry, and military. John Stack, NACA, for the scientific design and aerodynamic research. Lawrence Bell, Industry, for the design and construction of the vehicle. Chuck Yeager, Air Force, for the piloting skill to execute the experiment. The citations specifically honored Stack for research to determine the physical laws affecting supersonic flight, acknowledging that without his definition of the compressibility physics, the plane would likely have disintegrated or gone out of control. Despite the triumph of the X-1, Stack was dissatisfied. Flight testing was dangerous, incredibly expensive, and slow. The X-1 could only fly for a few minutes and test one specific configuration. To design a fleet of supersonic fighters, the US needed to test thousands of wing shapes, airfoils, and fuselage bodies. The blind spot in the wind tunnels remained the primary bottleneck in American aeronautics. The solution emerged from Langley's theoretical physics group. In 1946, physicist Ray H. Wright proposed that the choking phenomenon was caused by the constraining effect of the tunnel walls. He theorized that if the walls were not solid, if they had longitudinal slots cut into them, the air could expand outward as it accelerated, relieving the pressure and preventing the formation of the choking shock wave. Most senior engineers were skeptical. Wind tunnels relied on precise control of airflow. Cutting holes in the walls seemed like leaking the experiment. However, Stack, demonstrating his keen instinct for high payoff risks, backed Wright immediately. He allocated resources to build a small pilot model, a parasite tunnel, to test the theory. The pilot tests were successful. Stack then made a bold administrative move. He ordered the conversion of Langley's two largest high-speed facilities, the 8-foot HST and the 16-foot HST, to slotted throat configurations. This was a massive engineering undertaking. The 16-foot tunnel was repowered to 60,000 horsepower. The test section was rebuilt with precise longitudinal slots that allowed a specific mass flow of air to escape into a surrounding plenum chamber, which was then sucked back into the diffuser by the main fans. When the repowered 16-foot transonic tunnel came online in 1950, the results were miraculous. For the first time, a wind tunnel could accelerate smoothly from Mach 0.9 to Mach 1.1 and beyond without choking. The blind spot was gone. The strategic value of this invention cannot be overstated. It allowed the US to gain a decisive lead in supersonic design over the Soviet Union, whose engineers were still struggling with drop models and flight tests. In recognition of this monumental achievement, John Stack was awarded the Collier Trophy again in 1951. The citation read, "John Stack and Associates at the Langley Memorial Aeronautical Laboratory for the development and use of the slotted throat wind tunnel." Stack thus achieved a unique status in aerospace history. He won the highest award in aviation for breaking the sound barrier in the air, 1947, and then won it again for breaking the sound barrier on the ground, 1951. John Stack died on June 18, 1972, following a riding accident. His death marked the end of the heroic age of aerodynamics. Stack's legacy is defined not just by the trophies on its shelf, but by the physical reality of the aircraft that flies today. Unlike the celebrity pilots of his era, Stack operated in the background, in the roar of the wind tunnel and the quiet of the conference room. But his fingerprint is on every shockwave formed by every supersonic aircraft in history. He was the engineer who proved that the sky had no limit.